This video is intended to provide a little background on derivatives, second derivatives, partial derivatives, and the Laplacian operator. As we move forward and begin looking at how the groundwater system changes with time, it will be crucially important to have a basic understanding of these mathematical concepts. We'll start with derivatives. It's not important in this class that you know how to actually take derivatives, but you do need to know what they are, rates of change. As an example, let's think about position. Moving objects obviously have positions that change with time. So the derivative of position describes the rate of change of position with time, which is a concept that we are all very familiar with, velocity. Because position x changes with time, that's what putting time in parentheses means. It means that x is a variable that changes with time. We can examine the rate at which that change occurs, and we call this velocity. We write velocity dx dt. Here the d indicates change, and the only difference between dx dt and delta x delta t is that while delta indicates some actual change, for example 3 feet in 3 seconds, the d over here in our derivative actually represents an instantaneous rate of change. Or in other words, d represents what would happen if the delta became infinitely small and you just examined a tiny, like I said, instantaneous amount of time. Another way of thinking about this is if you were driving down the highway at 60 miles per hour, delta is like taking the entire hour to figure out that you've gone 60 miles, while d over here is like glancing at the speedometer and instantly knowing exactly how fast you're moving. So just to restate it, the derivative of position x with respect to time t is the rate of change of position dx dt, otherwise known as velocity. Of course, we can take this a step farther because we can also take the derivative of velocity and look at how velocity changes with time. So the derivative of velocity, the rate of change of velocity with time, is of course acceleration. Now, because velocity is the first derivative of position, when we take the derivative of the first derivative, what we're doing is actually taking a second derivative. So acceleration is the second derivative, that's what this d squared means, of position. So if you see nomenclature like this, if you see the d squared x dt squared, then you know that you're talking about the rate of change of a rate of change, just like acceleration is the rate of change of the rate of change of position. Sounds a little bit like a tongue twister, but hopefully it makes sense. Okay, so derivatives and second derivatives are super useful, but it often happens that we want to examine a feature that varies with respect to more than one variable. For example, hydraulic head can vary with position, sure, but it also varies with time. So it might be different on opposite sides of a field, but it might also be different after a rainstorm than before the rainstorm. When you want to examine how something changes with respect to multiple variables like space and time, then you need to consider partial derivatives. Partials are a subject that so far we've really only glossed over, acting as if they were the same thing as derivatives, which they almost are, as an example, let's go ahead and consider hydraulic head as a position in, as a function of position in one dimension and as a function of time. So we can write that. So here we have hydraulic head as a function of both distance and time. So to examine how this hydraulic head changes in space, we can take the partial derivative with respect to space. This is called a partial derivative, and this is the nomenclature, this curly symbol. It's called a partial derivative because it only describes one of multiple ways that the function changes. If instead we wanted to examine how the function hydraulic head changes with time, we would take the partial derivative with respect to time, like this. Moving from 1 to 3 dimensions, we can consider the partial derivative with respect to x, y, and z, like so. In fact, this is so common that we even have an operator, the del operator, used to delineate change in 3D space. Using this operator, the rate of change of hydraulic head with space can be written as del H, which is this. So again, this is the rate of change of hydraulic head with space. It gives you the 3D slope of the hydraulic head profile. We could actually take the derivative of this function a second time as well. And I know it just got a little bit more complicated, but here is that first derivative that we started with. And on the bottom, we have 3 segments that are all just written in different ways, but mean the exact same thing, okay? So we just took the partial derivative of the first derivative with respect to x, and the partial with respect to y, and the partial with respect to z, okay? And then instead of writing it with those partials all on the top, we just rewrote that as partial with respect to x of the partial of h with respect to x, and all of that can just be written as del squared h instead for simplicity and just to clean it up a little. So it's actually a little more difficult to intuit the physical meaning of the second spatial derivative than it was the second time derivative, which was acceleration, but we can still try. Basically, if the first spatial derivative of hydraulic head is the slope or the hydraulic gradient, then the second derivative describes the curviness of that slope. Now, perfectly linear gradients don't have any curvature, in which case the second derivative is actually going to be equal to 0. However, in nature, it turns out there often is some degree of curvature, some variability to this rate of change, and so the second spatial derivative actually helps us to pull out those variabilities, examine them, and use them to more accurately describe the system under study. So while the del operator indicates a change of position, a rate of change of position, the del squared or Laplacian operator indicates the curvature of that change with space. You will see this nomenclature in the text and should interpret it as the rate of change of the variable under consideration, or more simply, the curviness of the change in the variable. In our example today, that variable was hydraulic head, but it could just as easily have been changes in a physical property like hydraulic conductivity, which can also vary with space. This explanation has skipped over the actual calculus, but hopefully leaves you with a richer understanding of the principles underlying these mathematical concepts. If you want to see some examples of actually taking these derivatives for simple functions, check out Appendix B4 on page 627 of the textbook.